So we're ready now to be solving the trigonometric equations, starting with the basic trigonometric equations. That is, at first, let's solve equations like sine of theta is equal to a number, cosine of theta is equal to a number, or tangent of theta is equal to a number. And to solve those types of equations, you can follow the strategy that I have outlined for you in the typed lecture notes here. And this there's a lot going on here. You see, there's a lot of steps, a lot of things to consider. Okay, so try to break this down and consider how we are approaching this really from a geometric point of view, rather than just reading and memorizing lines of text here. I really hope that you'll be considering visualizing the problem using the geometries that we've been discussing throughout the course. The most relevant to the geometry that'll be useful for us here, I find, is the geometry of the unit circle. Using the unit circle, we can determine in which quadrants we would have solutions to a given trigonometric equation, and for each of the solutions that we would have within the quadrants of the unit circle, we can associate those solutions with some reference number. Quite often there would be one reference number for a variety of solutions. Usually two solutions within the quadrants of the unit circle will be associated by the same reference number. So we'll be wanting to use that notion of symmetry that we have to reference number within the unit circle. Right? So if we know the reference number, we can associate that with angles or arc lengths within any of the four quadrants of the unit circle in order to get solutions to these equations in the interval 0 to 2 pi if we're in radians, or 0 to 360 if we're in degrees. Then we're going to be using the other notion of symmetry from the course of periodicity in order to extend those solutions to all possible solutions. As in general, we're going to be solving equations here which will have an infinite number of solutions, an uncountable number of solutions. There's going to be also some cases where we can run into equations here which in fact have no solutions. A quick example of that would be the equation sine of theta is equal to 2. The equation sine theta is equal to 2 would have no solutions because the sine of theta cannot equal to 2. Recall that the amplitude of the sine function is equal to 1. Okay? So sine of theta is never going to be more than 1. But if we have an equation whereby there is at least one solution here, we can expect there's going to be many more. And in general, we're going to have infinitely many solutions. So symmetry is going to play a large role here, as will also the inverse trigonometric functions that we've discussed. The inverse trigonometric functions can give us one of the solutions to a given basic trigonometric equation. Okay? That's because, again, the inverse trig functions are themselves functions, and when you use a function, you get only one output. So even if we were to resort to the calculator for solving some of these equations here, the calculator can at best give us one solution, even when there's an infinite amount of solutions. So we still have to resort to the underlying geometry and the symmetries that we've discussed in the course in order to extend any one solution that we can find to finding all the solutions. Periodicity I refer to as the term for when we are going to be adding integer multiples of the period of the function. The basic sine function and cosine function have a period of 2 pi. So if we add 2 pi times any integer to any solution that we have, we should come to a coterminal solution, right? Back to another measure of the input, which would be in the same quadrant, for example, of the unit circle, by adding 2 pi, okay? Or 360 degrees times any integer. Now, the set of all integers can be expressed using the uppercase Z, which has a double bar in it, a double bar on the diagonal. So it's like a Z with a thick bar on it. Okay, that is the letter that we use to represent the set of all integers. Integers are the numbers 0, plus minus 1, plus minus 2, etc., etc. So we can write k is an element, we can read this statement as k is an element of the set of integers. And it's a more compact way of writing that we intend to choose any and all integer values for k. It's more compact than actually writing out the list of all the values, but that would also be sufficient. So you could say k is an element of this set, 0, plus minus 1, plus minus 2, etc., etc. So that way, when we write 2 pi k or 360 degrees k, what we're saying is that we're accounting for, let's take 2 pi k for example. If k is equal to 0, if we choose k is equal to 0, then 2 pi k would just equal 0, because 2 pi times 0 is 0. But if k was equal to 1, then 2 pi k would equal 2 pi. If k was equal to 2, then 2 pi k would equal 4 pi. If k was equal to, let's say, negative 2, then 2 pi k would equal negative 4 pi, etc., etc. If we chose k to equal 10, then 2 pi k would be 20 pi. Okay, and every time we choose an integer and multiply it by the period of the function, we would find a coterminal value, right? Because we would be going through a full period to get back, okay, to the location of another solution. Okay. These are all notions of symmetry, and it is really best to examine these by using the underlying geometry, as I stated. So you can use the geometry of the unit circle primarily. You can also use the geometry of the trigonometric waves, and sometimes we might even use the right triangle trigonometry, somewhere within these exercises as well. Now, being able to list specific solutions, after we have created a set of all the possible solutions, that there could be an infinite amount of solutions to an equation, we can then pick out specific solutions if we wish. One way that we can do that is we can choose particular values of k. All right, we can select specific values of k from our list of all the integers, and we can find values of theta or t or whatever the input variable is, okay, that would satisfy the equation. So for example, if our solution set is written as 25 degrees plus 360 degrees k, where k is any integer that we want, any and all of the values in this set, and if we are asked to find, let's say, 3 specific solutions, well, we can choose any three values of k that we want. Okay, maybe some of the most convenient values of k we might choose would be 0, plus, and minus 1, are the easiest to multiply by. If k was equal to 0, then theta would equal just 25 degrees. If k was equal to 1, positive 1 that is, then theta would equal 25 plus 360 times 1, which is 385. And if k was equal to negative 1, we'd have 25 minus 360. All of those would be coterminal, right? We can see that they are coterminal if we consider just where they would fit in the unit circle. If I could do a little sketch right here of our unit circle, for example. Right, if we were to plot where is 25 degrees in standard position, that would be right here. Okay, so we have theta 1 is equal to 25 degrees, this angle right here. Okay, that would put us at this terminal point right here, right? And that terminal point right there would have in its coordinates information about the trigonometric functions, for example. And then if we were to consider the solution 385 degrees, for example, well, that would mean that we would go through a full rotation and then back again, and that's going to put us right back at the same terminal point. So theta 2 is equal to 385 degrees. Okay, that would be represented then by this angle right here. It goes through a full rotation and then a little bit more. And theta 3, let's say, is the solution negative 335 degrees. Okay, that would, in standard position, rotate backwards this way and come back to here. Okay, and that would again be coterminal with the other two solutions. So the point is that all three of these terminate, okay, at the exact same point. Okay, so they could all be considered solutions to the same trigonometric equation. Okay, now what trigonometric equation could I be referring to? Well, let's take a look at a basic trigonometric equation here. Okay. Okay, just a basic trigonometric equation. And by basic trigonometric equation, I'm going to mean something like the sine of theta is equal to a number, where c is just representing a constant, so some number, or cosine of theta is equal to a number, or tangent of theta is equal to number. We could even consider the other three trigonometric functions because those are reciprocals. If we had something like, if we had something like cosecant of theta is equal to c, well, we could use a basic identity here. We could say, well, this is 1 over sine theta is equal to c, and that means that sine theta is therefore equal to 1 over c. So as long as we can do any of these three basic equations here, we can already start to consider how we could do trigonometric equations involving the reciprocal trigonometric functions as well. Okay, so let's start with just a sine function or a cosine function at the beginning. Okay. All right, let's solve the equation 2 cosine theta minus 1 is equal to 0. Okay. Okay, so I would call this a linear trigonometric equation. Linear because the trigonometric term is to the power of 1. Okay? So I'm going to say it is a linear trigonometric equation. Okay? Consider that, like, for instance, if I let x equal the cosine of theta, okay, and plug that into this equation, if I replace cosine theta with the variable x, then this equation just becomes this, turns into this, 2x minus 1 is equal to 0, right? A truly linear equation. All right, and this is an equation we can solve for x. Of course, this has the solution x is equal to 1/2. Okay, that's good. We can solve this as a linear equation to get x. But we actually want to know what theta is here, right? So if we were to solve this equation to get theta, right, we add 1 to the other side, and then divide by 2, just as we would have done here. We solve for the cosine of theta. Cosine of theta is equal to 1/2. Now we have to consider what are the solutions to that. Okay, so I outline the strategy for finding these solutions here, and your general strategy for expressing your solutions. Okay, trying to sort of condense this. Begin with the solutions that you would find in the initial period of the function. Use the unit circle to do so. The initial period. Well, the function that we're dealing with now is the cosine function. And the cosine function has a period of 2 pi, or 360 degrees. Right? So if we consider first, okay, let's say step 1, okay, find solutions in the interval from 0 to 2 pi. Start with that. Okay, I'm even open at 2 pi because then we can start another cycle at 2 pi. So within the initial period of the function from 0 to 2 pi, okay, let's find all the solutions we can, okay, in that initial period, and we'll use the geometry of the unit circle to determine where those exist. For each such solutions that we find from after step 1, we're going to add integer multiples of the period, as discussed. We'll add 2 pi times k if our solutions are in radians, and we'll add 360 degrees times k if our solutions were in degrees. Okay. For step 3, if the solutions happen to repeat, we'll express them in regular fractions of p. We'll take a look at some examples like that. Okay. Give me a couple examples. There's one in the notes we can take a look at. And then for specific solutions, choose integer values of k. I already mentioned that before. Right now, the instructions that I've given for this exercise are just solve. That is under the assumption then that we should find all the solutions to this equation. Okay. Find solutions, starting with finding solutions from 0 to 2 pi. Okay, for this equation right here, the cosine of theta is equal to 1/2. That is a basic trigonometric equation. The cosine of theta is equal to some constant c. In this case, that constant is 1/2. So within the unit circle, using the geometry of the unit circle, we'll do larger than that, okay. All right, y-axis, x-axis, quadrant 1, 2, 3, 4. Whereas the cosine of theta is equal to 1/2. Recall that for any terminal point with coordinates x, y, the x-coordinate is going to equal the cosine of theta, or the cosine of t. Theta would be interpreted as an angle here, right? And of course, the y-coordinate is the sine of theta. So we want to look in the unit circle for where the x-coordinate is equal to 1/2, because we have a cosine of theta is equal to 1/2. Well, we know that this point right here, for example, is the point with coordinates 1, 0. Where x would equal 1/2 would be halfway between the origin and this point, okay? But that's not a point on the unit circle, that's a point on the x-axis. But from there, I'm going to look up to where this intersects with the unit circle and look down to where this intersects with the unit circle. And here are 2 points on here, 2 terminal points. Let's call this one P1, okay? P1, whose x-coordinate is going to be 1/2. And its y-coordinate is, well, we can find out what its y-coordinate is by using the Pythagorean theorem, right? Just write that as y right now. We know that that y-coordinate is going to be, in fact, √3/2, right? And this point down here, P2, has an x-coordinate of 1/2, and it has its y-coordinate. Okay, I'll call it y2. We know that that's actually going to be negative √3/2, by the way, okay, because we've seen this enough. This is √3/2. This is going to be negative √3/2. But in general, we really only need to know one of the 2 coordinates if we're solving a sine equation or a cosine equation. Right. So we're using geometry here now in order to establish the quadrants in which we would find solutions. So in which quadrants do we find solutions to this equation now? We find there's a solution in quadrant 1, and there's going to be a solution that exists in quadrant 4. Okay? I'm going to call the solution in quadrant 1, this is a theta right now. Okay? This is theta. I'm going to call this solution here theta 1. Okay? And then there's solutions that can be found in quadrant 4. I'm going to call this solution right here, I'm going to call it theta 2. So I have a theta 1 to theta 2. The subscript doesn't have to do with the quadrant. It has to do with these are the individual solutions that we're finding, and these are each within the interval 0 to 2 pi. I'll make a note here. If we had chosen to instead do this, if we were to call that angle our solution theta 2, that is another solution that would be in quadrant 4. I just want to make a mention, though, that that solution would be negative, okay, which is fine when you're finding all solutions, but it doesn't find a solution between 0 and 2 pi, right? The interval 0 to 2 pi doesn't go to negative numbers. And so I'm referring to finding solutions initially that are going to be positive between 0 and 2 pi. Or if you're in degrees, this can be between 0 and 360 degrees. Okay? So, we have solved the given equation into the basic trigonometric equation form. Then we have drawn a picture of the unit circle and used geometry in order to figure out which quadrants contain solutions to our given equation. Now we want to use reference and other notions of symmetry in order to find the specific values of these solutions. Okay? We'll notice that by symmetry, that theta 1 and theta 2, okay, they have to have the same reference angle. They have to have the same reference angle, and that reference angle we can call theta bar or theta hat. Sometimes, right, sometimes the notation theta hat is used for reference angle. Okay, I'm going to use theta bar right here for the reference angle. Okay, and recall that quadrant 1, any solution that's already in quadrant 1, okay, where it's between 0 and pi over 2, is already equal to the reference angle. Okay. So we'll note that for this case, it turns out that theta 1 is equal to theta bar, okay, since theta 1 is contained within quadrant 1. If you didn't have a solution in quadrant 1, right, when would that happen? Well, let's say you were solving cosine of theta is equal to negative 1/2. If you're solving this equation, cosine theta is equal to negative 1/2, notice that when we draw our unit circle now, we would be looking for where x is negative 1/2. Right? That's where x is negative 1/2, here and here. And that means that we would in fact be in quadrant 2 and quadrant 3. So I may call the quadrant 2 solution theta 1. That would be this angle right here is theta 1. And then theta 2 could be the quadrant 3 solution. So that would be like this angle right here would be our theta 2, for example. So there's a quadrant 2 solution, a quadrant 3 solution. Again, those both have the same reference number, but recall that the reference number, if say we take the solution that was in quadrant 2, our theta 1, if you have a quadrant 2 angle, you can find the reference for it by subtracting it from pi if we're in radians. Right? Just in this case over here, for the equation that we've been working on here, we already had a solution that was in quadrant 1 and was already positive, so we already had the reference angle from that solution. Okay. All right, now what is the value of theta 1? Okay, there's a couple ways that we can find that. One is if we already know, okay, let's write cosine of theta 1 is equal to 1/2. Okay, where we already know theta 1 is in quadrant 1. If we know a quadrant 1 solution to this equation, then we can just use that. Okay, this is an output of the cosine function that we should be familiar with already at this point. Okay, we should, we might recognize this, for instance, as, let's see, in radians, what would this be? Pi over 3. Or in degrees, 60 degrees. Now, more generally speaking, so that we can solve equations where maybe we don't know what the output is really going to be, okay, we can also use the calculator. Okay, theta 1 is equal to the arc cosine of 1/2. All right. So you can try that on your calculator, if you will, right now, in order to find out what the solution is. Now, if you're set in radian mode, you'll most likely get a decimal value. Okay? And I would prefer the exact value instead. But in degree mode, in this case, in degree mode, you'll get a precise value of the 60 degrees. Okay? So make sure you can use your calculator in order to do that. Okay? To solve any one of these equations for one of your solutions. Okay, so we already have now one solution. We have found one solution to the original equation. Now, how many solutions does this equation actually have? Okay, consider the cosine wave. If we were to graph the cosine wave, do a little sketch of that. The cosine wave is the one that looks like this, right? Repeats like that indefinitely in both directions. Okay, it has a maximum of 1 and a minimum of -1. Right? This is the graph of y equals, let's say, the cosine of x, or the cosine of theta, for example. If I make this the theta axis, then that would be y equals cosine of theta. Well, then, when is the cosine theta equal to 1/2? Well, you want to also consider the graph of y equals 1/2, because when cosine theta is equal to 1/2 would be when the y value of the curve is equal to the y value of this line. Y equals 1/2 is a horizontal line, where the y coordinate is always equal to 1/2. Right? Anywhere where this red line, the y equals 1/2 line, intersects the wave, the cosine wave, Every one of those points is another solution to the equation that we were given. Cosine theta is equal to 1/2. And how many are there? Since the wave just keeps going and going indefinitely, there is in fact an infinite amount of solutions here that we're going to find. An infinite amount of them, an uncountable number of them. And the calculator only tells us one of those solutions. The calculator, even when we use the arc cosine key, we only ever get one of those infinitely many solutions. That's because the arc cosine was designed as a function, so that when you hit that key, you get one and only one answer. Right? And you get the same answer every time you use it for the same problem. So we need to find all the other solutions. Now, which was the solution that the calculator gave us? Look at it in the wave. The calculator gave us this solution right here, theta 1. Okay? On the wave, that would be this solution right here that the calculator gave us. Okay? That's the solution, pi over 3. Now we also want to know, right now, we want to know what is this solution going to be in quadrant 4, right? The theta 2. How do we find theta 2? That's quadrant 4. That's a positive quantity, less than 2 pi. That would be this solution right here, then, that we're looking for next. That one. Okay? After that, then we can start adding full periods to each. Notice if we add a full period to our first solution, a full period added to that would get us to this solution. All right? And then another full period added to that would get us to this solution. All right? So we can extend this. That's where we're going. We want to get from this solution by adding a full period, we'll get that solution. By adding another full period, we'll get to this solution here. By subtracting a full period from this, we would get that solution. By subtracting another full period, we would go back and get the solution prior to this. Okay. If we were to add a full period to this solution right here, okay, that full period added to that would give us this solution. If we were to subtract a full period from this solution right here, the quadrant 4 solution, it would get us back to this solution. Subtract another full period, it would get us back to this solution. So we're starting by finding initial solutions between 0 and 2 pi, and then we'll start adding and subtracting full integer multiples of the period in order to end up extending this to all of the solutions. We'll end up getting every single one of these. Okay. So we have found theta 1. Okay. We could have used an inverse trig function to do that as well. Okay. Now how do we find theta 2? Well, theta 2 is an element of quadrant 4, okay? And in fact, theta 2 is between 0 and 2 pi, so theta 2 has to be between 3 pi over 2 and 2 pi. And we already know that theta 2 has a reference number of pi over 3, right? So what is a quadrant 4 angle? Here's a picture to represent what we're saying here, the geometry here. Theta 2 is this amount of rotation, okay, such that the reference, that is the amount of rotation remaining, is equal to pi over 3. So using that geometric interpretation, we can see, well, this is how we can find theta 2, or the formulas that we've already looked at before in this course. Theta 2 is equal to 2 pi minus pi over 3. That's equal to, what, 6 pi over 3 minus pi over 3, which is 5 pi over 3. So we have theta 2 is equal to 5 pi over 3. Okay? Or That would be 360 degrees minus 60 degrees. That would be 300 degrees, in other words. Okay? Now that would be then our blue solution from up above. All right, this is our quadrant 4 solution. Okay, that is between 0 and 2 pi. Now you can check this in the original equation just to confirm that this actually works. Okay, to check the original equation, which was 2 cosine theta minus 1 equals 0, we check, does 2 times the cosine of 5 pi over 3 minus 1 equal to 0? Is that true? And then you make sure that you're in radian mode on your calculator, okay, and you can plug it into your calculator and find out. Okay, so I'm plugging it in my calculator right now, and I'm getting, yes, the cosine of 5 pi over 3 is exactly equal to 1/2, so this becomes 2 times 1/2 minus 1. Okay, that's 1 minus 1 equals 0, and that is true. So we did, in fact, find another solution. Just as pi over 3 would have been a solution, 5 pi over 3 is also a solution. Okay. So now we have the solutions found between 0 and 2 pi. That is really the majority of the work that goes into being able to solve one of these things. Okay. Now we can extend those solutions to include adding and subtracting integer multiples of the period. And again, the period of the cosine function is 2 pi, so we're going to be adding and subtracting multiples of 2 pi. Okay, so step 2 from that strategy is listed above. Okay, we're going to right now express all of the solutions. Okay, that is, we're looking now for the coterminal solutions. Right? So the angles which would terminate at the same points. Okay, in quadrant 1, right? So for theta 1, for instance, right, we already had 60 degrees. Okay, we also want to include what if we went through a full rotation and back again. Okay, or what if we went through 1, 2, 3 rotations and back again, or etc., etc. Or what if we went backwards instead? Right? What if we had, if this was theta 1, what if we wanted to consider, what about the solution like this, right? Which would be pi over 3 less than 2 pi, but in the negative direction, right? Or what if we wanted to be able to rotate backwards through a full rotation and back again? All of these possibilities that we want to find. Those can all be found by taking the initial solution at pi over 3, the initial solution in quadrant 1 at pi over 3, okay, and then adding k times the period, which in this case would be 2 pi is the period. Okay? And that would give us all the quadrant 1 solutions. K is an element of the set of integers. Okay? So that's to say that, in other words, that k is part of the set 0, plus minus 1, plus minus 2, dot, dot, dot. Okay, this pattern continues. So there's now an infinite amount of solutions which all would terminate in quadrant 1, and all would be solutions to the given equation. Let's do the same for theta 2. We had 5 pi over 3 already as one of the solutions. We can then add 2 pi k. Okay. Now, if we were doing this in degrees instead, okay, we could say theta 1 is equal to 60 degrees plus 360 degrees k. We could say theta 2 is equal to 300 degrees plus 360 degrees k. And let's remember also that when you're writing solutions in degrees, you need to write the degree symbol. Because if we don't write the degree symbol, then we are saying the measure is unitless. And if it's unitless, we always assume that we meant radians. Up here, I didn't have to write radians at all. Just wrote the number. Okay, but it's important that we actually write the degree symbol there so that the reader of your work knows that what you meant was degrees versus radians. It does make a difference. Okay. All right, so we now have found all the solutions. Okay. Now, as far as this notion of do these solutions repeat in regular fractions of the period, the way to look to see if they repeat is to plot out the different solutions and take a look at the angular measures to get from one to the next. Okay. Does it repeat in fractions, regular fractions of the period p? The period p here is 2 pi. So we plot the two solutions. We have a solution here in quadrant 1, and we have a solution here that is in quadrant 4. Okay. What I'm checking for is, as we continue to rotate in one direction from one of the solutions to the next, measure how much rotation we went through. This amount of rotation here is what I'm interested in. And then I want to compare that to if we continue rotating in the same direction, but from the other solution, all right, to the next one, okay, which in this case would be back to the first. Okay, I want to consider that amount of rotation. If these are both exactly the same amount of rotation as each other, then I would say that we have repeats. Okay, and that is not happening in this case. The only way to have repeats when there are in fact two solutions, okay, when there are two solutions, if you have a repeat, then they would have to be separated from each other by 180 degrees or pi radians. So for instance, if we had an equation which gave us a solution here that was in quadrant 1, and another solution here that happened to be in quadrant 3, okay, it would have to be the case that if we measure the amount of rotation from one to the next, if that amount of rotation between them was exactly equal to pi radians, and then the amount of rotation to get from the second one back to the first one would of course also be pi radians, because these each have the same amount of rotation to get from one to the next when moving in the same direction, these would repeat. And in that case, if that were the case, okay, let's say this solution here was our theta 1, and let's say that this solution here was our theta 2. Okay, then we would say, oh, but theta 2 then is just equal to theta 1 plus pi. In other words, we could just say that theta 1, okay, that all the solutions, let me say it this way, all the solutions could be expressed as theta 1 plus k times pi. Okay, and this would be our complete solution set in a case where we had these repeats here. The idea is that instead of having to write out the solution set for theta 1 and the solution set for theta 2, whereby we're adding 2 pi k to each, okay, we could instead condense that into a single set whereby we're taking just one of those two solutions and adding, instead of adding 2 pi times k, we can add just pi times k. Okay. So in this case, for instance, we had, what did we have? We had theta 1, let's go to degrees. Theta 1 was 60 degrees, right? But theta 2 was 300 degrees, right? So in degrees then, what was the measure of this rotation right here? Right, from 60 degrees to 300 degrees, that means we would have to go through 240 degrees of rotation to get from here to here. So we would have to add 240 degrees to theta 1 in order to get to theta 2. Then, to continue in the same direction to get from theta 2 back to theta 1 again, we would go through this much rotation. That would be an additional 120 degrees of rotation. Okay, so these two quantities don't equal each other. If these were both equal to 180 degrees, then we could combine our two sets here into just one set of solutions, which would say, where we would add 180 degrees times k or pi times k. Okay, so these are simplifications that we can do when we have multiple solutions, if we want to try to combine them into fewer sets of solutions. Okay. Take a look at a couple examples from the lecture notes, or at least one example from the lecture notes whereby we can do that. Okay. 4. For specific solutions, choose integer values of k and solve for theta. So this is if we were asked to find specific solutions, okay, we could do so. So let's say we wanted to list specific, let's choose some. List 4 specific solutions to the equation 2 cosine theta minus 1 is equal to 0. Let's say we wanted to do that. Okay. Oh, and up here we would say, so 240 degrees does not equal 120 degrees. So we have no repeats. Okay. No repeats in regular fractions of p. Okay, so we're not going to combine or adjust our solutions. We're done with the solutions. We have solved for all the solutions now, okay, for the original equation. Right? So these two sets here, this gives us all of the solutions, an infinite amount of them. All right, but now let's list 4 specific solutions. How do we do that? Choose specific values of k. I would like to choose k is equal to 0. Okay? If k is equal to 0, then that gives us theta 1 is then going to equal just pi over 3, because pi over 3 plus 2 pi times 0, well, that would just be pi over 3. And theta 2, if k is equal to 0, theta 2 would just be 5 pi over 3. Okay, so those would be 2 specific solutions. We need 2 more. Let's choose k is equal to 1. If k is equal to 1, then theta 1 is going to equal pi over 3 plus 2 pi. And pi over 3 plus 2 pi would be 7 pi over 3. And theta 2, if k is equal to 1, theta 2 would equal 5 pi over 3 plus 2 pi, and that would equal 11 pi over 3. So we now have 4 solutions. All right? We have pi over 3 and 5 pi over 3. That's 2 solutions there. Right? We also have 7 pi over 3 and 11 pi over 3. Okay, pi over 3, 5 pi over 3, 7 pi over 3, 11 pi over 3 would be 4 specific solutions. We could keep choosing values of k to find more and more specific solutions, as many as we might want. Okay, so step 4 is about if we wanted to find a finite set of solutions. In step 2, of course, we were finding all of the solutions to the equation. Okay, once we have all the solutions, we can start to pick out individual ones. Okay, so that's going through the details of solving any one of these basic trigonometric equations. That's once you have an equation that says the sine of theta is equal to a number, the cosine of theta is equal to a number, or the tangent of theta is equal to a number. In fact, you could even do the same thing if you had cosecant, secant, or cotangent by just writing it using a reciprocal identity. The point is, once you have one of these 3, you can already start solving the associated equation for all solutions by this process. Okay. All right, let's try another one. Let's try one that goes through a modification. How about a horizontal shift? Okay. Solve the sine of x minus 60 degrees is equal to, I'll do a negative number here. Okay, x minus 60 degrees is equal to negative 0.3. Okay, so we have a horizontal shift here, if we recall from the graphs of sine functions, for instance. Right? Now this one's in degrees, so we're going to get solutions that will be in degrees as well for this. We should expect solutions in degrees. Okay? In order to solve this, okay, I'm going to make this look a little bit more like an equation like we've already looked at. I'm going to choose theta to replace the argument here. If I let theta equal x minus 60 degrees, then notice that that allows us to rewrite the equation as the sine of theta is equal to negative 0.3. And so we have the sine of theta is equal to a number, which is a basic trigonometric equation. Now consider, using geometry, right? How we can find solutions. Here we go. All right, how we can find solutions to this equation right here. I'm going to use the geometry of the unit circle again. Okay, remember in the unit circle, the y coordinate for any terminal point, okay, x is going to be the cosine of the theta and y is going to be the sine of theta. So it's the y coordinate that is equal to the sine of theta. So we want to know where y, okay, where y is equal to negative 0.3 within the unit circle. That is that we want the sign to be negative, right? The sign is going to be negative, right? Let's see, if this is like down here, if this is the point 0, negative 1, then negative 0.3 maybe is around here or so, right? Negative 0.3. That would intersect the unit circle here and here in terms of a y coordinate, right? So we can already see there's going to be a solution that is found. All right, use different colors for that. There's going to be a solution found in quadrant 3. I'll call that theta 1. Theta 1 is in quadrant 3. And there's going to be a solution found, it looks like, in quadrant 4. Okay, so quadrant 4. Call that theta 2. All right, so we want to find those two solutions in the interval from 0 to 2 pi. Well, ultimately, we want to find all the solutions. Okay, so in this case, I'm going to want to find some representative okay, just find some representative okay, theta 1 solution and find some representative theta 2 solution, and then we'll find all solutions by adding integer multiples of the period. So how can we find some value of either theta 1 or theta 2? Well, one thing that we can do is we can solve the equation sine of theta is equal to negative 0.3 by using the arc sine function. That's theta is equal to the arc sine of negative 0.3. Okay. So let's go to the calculator. We can find out the solution to this. Right? We're going to want our solutions to be in degrees so that we can deal with this horizontal shift. So we make sure the calculator is set to degree mode. So we find the arc sine of negative 0.3. And I'm getting in degrees that this is approximately negative 17.4576. So I'll go to 2 decimal places here. Negative 17.46. That would be a measure of degrees. Recalling when we're dealing with the arc sine function, the arc sine will always give us outputs that are in either quadrant 1 or quadrant 4. Which quadrant is this solution in? It's the quadrant 4 solution. So what we have here is a representative of theta 2 because of the quadrant that it shows up in. Right? This is a quadrant 4 solution we just found for theta. Okay. All right, so theta 2 is approximately negative 17.46 degrees. We can extend by adding integer multiples of the period to that. But what about the quadrant 3 solution? Well, notice that theta 1 and theta 2 have the same reference angle, right? They have the same reference angle as each other, call it theta bar. What is that reference angle? Well, now that we already have a solution for theta 2, negative 17.46 degrees, we can find its reference, and its reference would be the rotation back to the x-axis. Okay, and that amount of rotation would be positive 17.46 degrees. That is the reference number. Okay, now find theta 1. Okay, so theta 1 is a quadrant 3 angle. Okay, it's a quadrant 3 angle, and it has a reference of 17.46 degrees. So we push that reference into quadrant 3 by adding 180 degrees. So 180 degrees plus 17.46 degrees. and that gives us 197.46 degrees. And that is a representative, then, of the quadrant 3 solutions. Okay. So we now have one quadrant 4 solution and one quadrant 3 solution. Now we can extend to find all solutions for theta. Okay. Find all theta solutions. Okay. So theta 1, the set of theta 1 values would be 197.46 degrees plus 360 degrees times k. And theta 2 would be, we can use the negative 17.46 degrees, which was a representative. We weren't told it had to be positive in the instructions, so we can use that. And then add 360 degrees times k. So these would be values of theta that would satisfy the equation that has theta in it. But the original equation didn't have theta in it. The original equation had x in it, and we chose this substitution right here. Okay, I'll outline that in a different color so that it stands out a little better. This was our substitution we had selected in order to set up a more basic trigonometric equation. We have to solve for x now. Okay? Given that theta is x minus 60 degrees, okay, what is x going to be? Okay. So now we have to find all the x value solutions, right? Given that we said that theta was x minus 60 degrees, then that means, solve this equation for x, it means theta plus 60 degrees would equal to x. Right? So we can find out what x is. Let's say I find x1, for instance. x1 would equal theta 1 plus 60 degrees. Right? x1 is equal to theta 1 plus 60 degrees. Okay. And we already have theta 1 right here, 197.46. Okay? So you take 197.46 and add 60 degrees to that. We'll get 257.46 degrees. And then plus 360 degrees k. That gives us an uncountable number, an infinite amount of solutions, okay, for one of our x values, okay, our x1. And then x2, well, x2 would equal theta 2 plus 60 degrees. Right? Theta 2 plus 60 degrees. So we take theta 2, which was negative 17.46, and we add 60 degrees to that. Okay, so 60 minus 17.46 will give us 42.54 degrees approximately, okay, plus 360 degrees k. Okay. All right, and these are the solutions that we were after. Okay, so let's say we wanted to list some specific solutions. Okay, let's say we wanted to list 4 specific solutions x. Let's say we start with k is equal to 0. If k is equal to 0, then x1 is equal to 257.46 degrees, and x2 is equal to 42.54 degrees. Then let's say we choose k is equal to 1. If k is equal to 1, then x1 would equal 257.46 plus 360. All right, so what's that? 257 is 617.46 degrees. Okay, and x2, if k is equal to 1, we would get 360 plus 42 is, what, 402. So 402.54 degrees. So that would be 4 specific solutions. All right, so we should be able to check any and all of those solutions in the original equation to see if it works. Original equation was sine of x minus 60 degrees equals negative 0.3. We rounded our answers here, so we're going to get approximately negative 0.3 if this works out. So let's check in the equation. Right, again, sine of x minus 60 degrees is equal to negative 0.3. Use your calculator in degree mode. So let's start with x1. Sine of 257.46 degrees minus 60 degrees, does that equal negative 0.3? First, you're going to subtract 60 from 257.46, and you're going to get 197. So you get the sine of 197.46 degrees. Okay, checking the sine of 197.46 degrees. And I get that that's approximately negative 0.3000399.062, which is certainly approximately negative 0.3. Okay, similarly, you can check it for the remaining values here to make sure that it works. Okay, so that's how we can solve by the use of a substitution. We can solve when there is a horizontal shift or a phase shift in our trigonometric equation. Okay, the same process really could work also if we had a frequency modulation here. So if there was a factor in front of x, for example, we could use a substitution to help solve that as well. Right? We won't see any of those in this particular section, however. All right, so what's left? Using factoring strategy and quadratic. So there's some examples like that also in the notes right here. I think also I want to take a look at repeating solutions. Oh, here's a tangent example right here. Right? For the tangent, just recall that the tangent has a period of pi, not 2 pi. So for the tangent, right, again, you can find the initial solution by using the arctangent function. Okay? You should note what quadrants your solutions would be in. Okay, but whatever your solution is for the basic tangent equation, you would add integer multiples of pi, or 180 degrees, integer multiples of 180 degrees. Okay, because the period of the tangent function is equal to pi. Okay? So in other words, for a tangent equation, you don't need to find solutions in all 4 quadrants. You really only need solutions in 2 of the 4 quadrants. Like quadrant 1 and quadrant 4 would be, generally would be sufficient. Okay, here's another one with a horizontal shift incorporated into it, along with, having to solve it as a linear equation. So a combination of the 2 examples that I already worked on. Here's an example whereby you have no solution. Why? Because the sign is only ever going to output values between negative 1 and positive 1. Right? It can't be larger than 1 unless there was an amplitude modulation, and this is not modulated by an amplitude here. Okay, here's an example whereby we can have repeated solutions. The cosine squared theta is equal to 1/2. Let's take a look at that geometrically. So repeated solutions. Consider cosine squared theta is equal to 1/2. When we solve that, which this is a quadratic, you can use the square root property. That's cosine theta is equal to plus or minus the square root of 1/2. And now the square root of 1/2 is 1 over root 2, which when you rationalize that denominator, you get root 2 over 2. Right? Very common number for us to get as an output in trigonometry. Now cosine theta is equal to plus or minus root 2. That means we have 2 basic trigonometric equations to consider. The cosine of theta is equal to the square root of 2 is one of them, and the cosine of theta, square root of 2 over 2, and the cosine of theta is equal to negative the square root of 2 over 2 is the other equation. Okay. All right, so we have first, if the cosine theta is equal to positive root 2 over 2. Okay. We would have solutions to that. Remember, the cosine is the x-coordinate, okay? So the cosine is positive here in quadrant 1 and quadrant 4. So, okay, so this has solutions in quadrant 1 and quadrant 4. And in fact, as you can see from the work here, okay, you're going to have, theta 1, that solution, it turns out is pi over 4. And, your theta 2 for this basic trigonometric equation, one solution for that could be negative pi over 4. Another solution for that could be 5 pi over 4 if we take it as a positive quantity from 0 to 2 pi. So that's a possibility. Okay. Now the other equation here, the other basic trigonometric equation, we'll do these solutions in blue, cosine theta is equal to negative root 2 over 2. What quadrants would contain those solutions? Okay, cosine is negative in quadrant 2 and quadrant 3. Okay, so we have this solution right here. That would be 3 pi over 4. Okay, and then we have a quadrant 3 solution here. So let's say this rotation right here. Okay, sorry, that would be 5 pi over 4. Oh, I said this is 7 pi over 4 over here. Okay. So pi over 4, 3 pi over 4, 5 pi over 4, and negative pi over 4, or 7 pi over 4 if you wish. Okay, either one. We want a representative within each quadrant. That's the idea. Okay. Now, we have a total of 4 solutions within one complete rotation. So we have 4 solutions, okay, in one rotation. For example, from 0 to 2 pi, okay, we have the solutions, again, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay. And if we plot those 4 solutions out, okay, it just so happens that if we were to measure the amount of rotation from any one of these solutions to the next solution, for instance, this right here, okay, we get, between any two of these solutions, we're always going to get the same amount of rotation, as it turns out, because these just happen to be symmetric. This is not guaranteed just because we have 4 solutions. It happens to be the case because of the symmetry of these solutions. For instance, from pi over 4 to 3 pi over 4, the amount of rotation between them would be pi over 2, or 90 degrees, right? We have 90 degrees of rotation between the two. Okay. Then if we measure the rotation from 3 pi over 4 to 5 pi over 4, that amount of rotation is also pi over 2. And from 5 pi over 4 to 7 pi over 4, that amount of rotation is pi over 2. And from 7 pi over 4 back to, well, this would be then 9 pi over 4, okay, but back to this solution, that would be another rotation of pi over 2. Okay, so these solutions are all separated from each other by pi over 2, and to get back to to a representative of the original solution, right, we would have to get, add pi over 2 again. In fact, we would actually go to 9 pi over 4 if we did that, which would be coterminal with pi over 4. So all 4 of these solutions are separated by an equal amount of rotation. So we can combine the solutions, therefore. That is to say that instead of having to write pi over 4 plus 2k pi, 3 pi over 4 plus 2k pi, 5 pi over 4 plus 2k pi, and 7 pi over 4 plus 2k pi, instead of having to write all of that out, we could instead choose any one of these solutions that we want. Let's say I take pi over 4, without loss of generality, we can do that. And instead of adding 2k pi, we can instead add integer multiples of the amount of rotation between solutions. So k times pi over 2. Okay, so pi over 2 times k. And that would be it. K is an element of the set of integers. Okay, so this one statement right here, in fact, contains all of the information in these 4 statements up here. By exploiting the symmetry, the rotational symmetry we have here between these solutions that we have. Okay, so you can combine into a more condensed set of solutions if the set of solutions that you have to work with are all separated by exactly the same amount of rotation. Okay? Just because you have 4 solutions doesn't guarantee that they're going to be separated by the right amount of rotation. Here's an example. If I had a solution that was like at 30 degrees and another solution that was at, say, 150 degrees, and then another one that was maybe at 210 degrees, and then another one that was at like 330 degrees, for instance. So we have 4 solutions in 4 quadrants, right? But it doesn't satisfy that kind of symmetry. If we take a look at the rotation between them, from one to the next, from 30 to 150, that would be 120 degrees in rotation. But to get from, let's say, 150 back to 210, you only go through 60 degrees of additional rotation. And then from 210 to 330, you go through 120 degrees, and then from 330 back to 30, there would be another 60 degrees of rotation. So it's not the same amount in between successive solutions. So this would be a case where there is no significant repeat. Okay? You could combine the 30 degree and the 210 degree into one solution by saying that 30 and 210 are separated by 180, and the 150 and the 330 are separated by 180. And by the way, in general, these are all just suggestions for what can be done in order to help simplify your answers, and not necessarily requirements. Okay, but so that you're able to read solutions correctly, and as you're moving ahead, so that you can be able to write your solutions in more compact forms as well. Okay, I'd like you to at least be familiar with using these notions of symmetry in order to simplify your solution sets. Okay, so other than that, we have some examples in here of factoring that we can do. Okay, you can use a substitution, you can do some factoring technique. Take a look through that solution set right there, or this solution right here. All right. Rewrite the equation here as a standard quadratic. Put that quadratic in standard form. Do factoring strategy. If you know how to solve a quadratic equation, then you have the means to be able to set up solutions for these trigonometric equations here. Okay? Now we would get a set of, in this case, 2 trigonometric equations, and we can solve each of those independently. Each one of them is going to have an infinite amount of solutions. Okay. Now if we take it to, alright, so sine theta is equal to 1, for instance, that only occurs in the unit circle at the point 0, 1, so it only occurs at pi over 2. So you get pi over 2 plus 2k pi. And for the sine theta is equal to negative 1/2, you have solutions, right, where sine is negative, that would be quadrant 3, such as 7 pi over 6, and quadrant 4, such as 11 pi over 6. Add 2k pi to each. So you get this set of solutions right here. So we have 3 solutions to that particular equation right there. Okay. Do we have repeats? Can we express those by repeats? Okay. If we have the solutions at, let's say, pi over 2, okay, was 1, 7 pi over 6. Okay, that would be this rotation right here. That was pi over 2 right there. And 11 pi over 6. Okay, can we express these using repeats? Well, from pi over 2 to 7 pi over 6, for instance, what's the amount of rotation there? Okay, 7 pi over 6 minus pi over 2. Okay, is what? 7 pi over 6 minus 3 pi over 6, which is equal to 4 pi over 6, or 2 pi over 3. So this is 2 pi over 3, the amount of rotation here. And then how about from 7 pi over 6 to 11 pi over 6? 11 pi over 6 minus 7 pi over 6 is equal to 4 pi over 6, and that is also 2 pi over 3. And finally, to get from 11 pi over 6 back to something coterminal with pi over 2, okay, what would be the amount of rotation? So what's coterminal with pi over 2 after one complete rotation? 2 pi plus pi over 2 would be 5 pi over 2. Okay. Subtract from that 11 pi over 6. That is, let's see, 15 pi over 6 minus 11 pi over 6. That is 4 pi over 6, which is another 2 pi over 3. So we would, in fact, have an equal amount of rotation, okay, between successive solutions here. So that means, although I've expressed it here as 3 sets of solutions, you could express this as one complete set of solutions, whereby we can choose any one of the original 3. For instance, I'll choose pi over 2, just the first one in the bunch. And instead of adding 2k pi, and instead of adding 2 pi times k, we can instead add 2 pi over 3 times k, where k is any integer. And that would in fact include all the solutions that I've expressed here as 3 sets of solutions. For instance, if k is equal to 1, this is going to, pi over 2 plus 2 pi over 3 is going to give you 7 pi over 6. If k is equal to 2, then this is going to give you the 11 pi over 6, for example. Okay. All right, so you have some factoring strategy to work with here, which can get you a set of more than one basic trigonometric equation to solve. You know how to solve basic trigonometric equations now. Okay, so just to get you set up on another one, let's say you had, let's throw a secant in there. Secant of theta times the cosine of theta minus root 2 is equal to 0. We have a product of factors. Let's say we set secant of theta, the first factor, equal to 0, and set the second factor, 2 cosine theta minus root 2, also equal to 0. Secant of theta is equal to 0. You can, consider this geometrically or using reciprocal identity. This means 1 over cosine theta is equal to 0. But if we multiply both sides by cosine theta, okay, this means 1 is equal to 0, which is not true. This is a false statement. In other words, this particular equation has no solution to it. So it gives us no extra information. Something like secant theta is equal to 2, that would have solutions to it. You can find secant theta is equal to 2 by considering where the cosine of theta is equal to 1/2. Right? Again, by using the reciprocal identity. So this means the only solutions to this equation that are relevant would be solutions to this. That would be where the cosine of theta is equal to root 2 over 2. Okay, a basic trigonometric equation. Again, cosine is going to be positive if we are in quadrant 1 or quadrant 4. Okay, so we have theta 1. Okay, we have a theta 2. All right. And those solutions then are going to include in radians would be pi over 4 plus 2 pi k for the quadrant 1 solutions, and theta 2 we could say, how about negative pi over 4 plus 2 pi k. Okay, and that would be all the solutions, and therefore that would be all the solutions to the original equation. Okay. All right, so try out the homework. Let me know if you have any questions on that. I'll be checking my email. Otherwise, you can also let the tutors know at the tutoring center if you need any help as well. Okay, take care.